we really finished up there last time talking about reactions that they undergo. So just to remind everybody, they do follow what are referred to as addition reactions. So alkenes basically go through addition reactions. And what does addition reaction basically mean is instead of a substitution reaction like we talked about with alkanes, in a alkene, we are going to be adding two things into it. And where does it add? It always adds in the same spot on the alkene. It's always the carbon-carbon double bond. So the basic thing that we do is we basically add something to it. In order to make room for it, we turn the double bond into a single bond, and that allows one thing to be added to each carbon. So that's really a critical point. Double bond becomes single bond, and we add one thing to each of the carbons. And that's how pretty much all addition reactions occur, regardless if there's a lot more carbons on each side. It's always just the carbon-carbon double bond as to where that occurs. There's what is referred to as symmetrical addition. And symmetrical addition basically is when we add two of the same thing. And what that means is, for example, we add something like H2, Br2, Cl2. Pretty much each of the carbons are going to end up with one of those guys on each of them. Since they're both the same element, it doesn't really matter where that ends up. So we could have, something like this. And we add something like H2, which is known as a hydrogenation reaction. And basically, as we talked about last time, the nice thing about these is you pretty much have your structure there. So you just want to really, without thinking about it, just redraw what's there. Again, you really shouldn't change anything. Nothing weird happens. We're just going to redraw exactly the way we have it. The only thing that does is this part right here. We're just going to make it into a single bond. Everything else is exactly the same. And now what we've done by making that into a single bond, as we talked about, is we've now made room for one hydrogen to go here and one to go here. And we go from an alkene to alkane, and that is basically an addition reaction. So, it's really very simple in the sense that, you shouldn't try to do anything weird with it. Just basically redraw what you have. So for example, if I had, actually, that's a bad example. Let me draw it better there. Get rid of that guy. There we go. And I add two BRs here, BR2. Same thing's going to happen. We're just going to redraw this exactly the way it is. Again, I'm not going to get fancy with it. I'm not going to try to do anything weird. I'm just going to redraw it, making double bond into a single bond. And that's right there, into a single bond. Again, by doing that, what that's going to do is free up a space on the carbon and second to the end, and also free up a space for the carbon at the very end. And what's going to go in that space is, this is Br2, which is basically BRs. One BR there and one there. So these are symmetrical additions. Again, you can't really screw it up. The same element goes to each of the carbons. There's no worries about which one goes where. Any questions on symmetrical additions here? Now, we also talked about some additions that are what are sometimes referred to as being unsymmetrical. And an unsymmetrical addition, we essentially add hydrogen and something else like HCl, HBr, and even water. And we think of water as H and OH. And in an unsymmetrical addition, the hydrogen always ends up at the carbon that started with the most hydrogens. So that is where the hydrogen should end up, is again at that carbon that started with the most. And that's what's sometimes referred to as Markovnikov's rule. So for example, here, if we had this guy, and let's say we added water, for example, or actually we'll do, say we added HCl. Usually this involves some type of acid or something to help it out. But the exact same thing is going to happen here as we've been talking about. Absolutely nothing is going to change other than right there. And it's going to change the exact same way as we've been talking. We're just going to make it into a single bond. And the point of that is to allow room for this addition to occur. So turning our double into a single. And now we need to decide where these guys should go, because this is an unsymmetrical addition. And what that means is the rule is the hydrogen will end up at the one that started with the most hydrogen. So the carbon on the right had 2 hydrogens directly attached to it. The hydrogen on the left had only 1 hydrogen directly bound to it. What that tells us in this particular case, the hydrogen should end up over here. And that would give us what is referred to as the major product. Hydrogen would go here. The other part of it would go here. Again, opposite carbons, hydrogen to the one that started with the most. This is what would be referred to as the major product in this case. If you did the minor product would pretty much be the same thing except opposite in that particular case. This is another example. If we looked at something like something like this, and do this, and then this. And let's say we added water to this. Again, water can be thought up as hydrogen and OH, basically. So we would not change anything else on this molecule except for right here. So always this is what you would want to start with, is simply copying what's there. And that's, again, the best way to do it because it's kind of there for you. So again, I'm not going to change anything other than what we've been doing before, which is turning that double bond into a single bond. And that would be right about here, becomes a single bond. And now, and again, I didn't draw out the last guy just to make it uniform. I'll draw them out. At this point, we've now made room for H and OH to come onto these carbons. So we do need to analyze this again. We want to look for whichever one has the most hydrogens to begin with. So when we look at the carbon-carbon double bond to start, this carbon has 1 hydrogen. This carbon has absolutely no hydrogens attached to it at all. Again, not directly attached, which means the hydrogen in this case should end up at this carbon right here. And that's exactly what we would do. We would take the hydrogen and put them here. The other part of water would then be an OH, and we just made what is known as an alcohol because it has the functional group of OH. So these are what are referred to as unsymmetrical additions. And basically the hydrogen always ends up at the carbon that started with the most hydrogens to begin with. The other guy ends up at the other spot. Question on these types of reactions. Again, I can't tell you how important it is not to complicate it. So again, you have pretty much 98% of the structure drawn for you. You pretty much just need to recopy it and change the double to a single, add 1 to each carbon. Any questions on these types of reactions? Okay. So to finish up this chapter here, I think we're got a couple things left to talk about, which is aromatic compounds. So we're going to talk about aromatic compounds now. Aromatic compounds are really compounds that contain benzene. And what is benzene? It's really this structure right here. It is sometimes drawn like so. It's basically a 6-carbon structure in a ring, but it does have 3 double bonds in it. Or you could draw the resonance structure for it, which looks something like this. Or sometimes benzene is just drawn with kind of like a circle in the middle. And that's because these double bonds are delocalized, which means they are moving around and around. Sometimes they may be like on the left, sometimes it may be like on the one on the right. So sometimes people will just kind of shorthand it and draw that little circle in there. But it does stand for benzene, which is C6H6, 6 carbons and 1 hydrogen. There's essentially 1 hydrogen at each of these carbons right here. Important to remember, it is not cyclohexane because, again, it has those double bonds that are there. It's an aromatic compound. It's got those 6 carbons, and again, represented in a variety of places. Although a lot of times in our types of books, they oftentimes will use this structure to represent it, but you can't have the 3 double bonds that are there. Now, there are some historical type names that have benzene and some type of group attached to it. This right here is one of them. It has a methyl group, and this is what is historically known as toluene. Some people also just call it methyl benzene because it has a methyl group on a benzene. But most people, if they see that, will call it toluene. It's kind of an historical name that is used very, very commonly. This as well, this is aniline, also, again, a benzene ring with a nitrogen-containing group. And that's a historical name, sort of, that's used a lot. And this is an alcohol that contains benzene. This is phenol. And again, it's the benzene group with the alcohol group on it. So it ends in that OL. So we number these guys or give the names when they're, we not sort of an historical name by putting them in order with lowest number. Because there's 3 double bonds, you could pretty much start counting anywhere. So with only 1 group attached, we simply call this chlorobenzene. Again, no need to, no need to put the number of the chlorine. It's assumed to be carbon number 1. This is 1,2-dibenzene, dichlorobenzene. Again, the location of this guy and this guy given because there's more than 1 group. There's also 1,3-dichlorobenzene, again, 1 and 3 as you start numbering clockwise, and 1 and 4-dichlorobenzene as well. Now, these locations on a benzene ring are also important because they also have some names. The 1,2 location is what is sometimes referred to as the ortho location, or O, and sometimes people will just go O-dichlorobenzene, again representing the location of 1 and 2. The 1,3 location is what is referred to as the meta location. She's going to write that right. Come here. Meta location. And that would be M-dichlorobenzene. And the 1,4 positioning of these groups on a benzene ring is what is known as the para positioning, and that it would be P-dichlorobenzene. So again, we get rid of the numbers in favor of para, meta, or ortho with a 1,2, 1,3, or 1,4 positioning. So you should be familiar with ortho is 1,2, meta is 1,3 positioning, and 1,4 is para. And again, this is specifically for on a benzene ring, the positioning of two groups on that benzene ring. And those names are used a lot as well. Any questions on that there? So when toluene, phenol, or aniline has a substituent, the carbon groups attached to the methyl hydroxylamine is group number 1. So just to sort of highlight it for you here, these are some of those historical guys we were talking about. So this whole thing right here is aniline. And that's where this part of the name is. Again, where the nitrogen would be group carbon number 1, and the bromine becomes carbon number 3. This part right here, the benzene ring and our OH group, is where the phenol part of the name comes from. Again, that being carbon number 1. Going counterclockwise gives us the smaller numbers. If we went clockwise, we would have numbers at 4 and like 6, as opposed to 2 and 4. So again, we want the lowest numbers. So that's why we go that way. Again, naming the groups. And toluene is this part of it. So that part is the toluene part. And again, at that point, again, the methyl is carbon number 1 in terms of the ring, and we number everybody else accordingly. Going clockwise here, looks like we get a 2, a 4, and a 6. And going counterclockwise would get us the same sort of numbering. So it really doesn't matter in this case. You kind of go either way. And again, the rest of the groups are numbered accordingly. Questions on that there? All right, so let's take a look at this one here. Let's select the name for each of these groups, or each of these compounds. Again, the first thing is here we have a benzene ring, and we have a 1 chloral group attached. So that would be basically chlorobenzene. Remember, this is not cyclohexane because there's double bonds. We don't need the number because it's the only group attached. So it would be chlorobenzene in this particular case. Any questions on that one? Looking at our next one here, we got location 1, 2, and 3. So we have a 1, 3. Those are both methyl groups, dimethyl, and that would be benzene in this case. And it looks like that would be numbers or letter C. This is also the 1, 3 positioning. This would also be meta. RM, dimethyl benzene. You could even call it 3-methyl toluene, as that's toluene as well. So again, in organic chemistry, there can be multiple names for the same thing. But again, probably for us, this is probably the right name. And also, again, recognizing that that is the meta location of those groups. Any questions on that? All right. That should wrap this chapter here. Any questions on alkenes, alkynes, aromatic compounds, which basically contains benzene? Okay. Then we're going to roll into chapter 12 then, and we're going to start talking about alcohols, thiols, ethers, aldehydes, and ketones. A lot of this group, a lot of this chapter basically contains some carbon oxygen type bonds, single bonds with like an OH, carbon oxygen double bonds are in here. Thiols, though, does have actually sulfur groups attached. So we'll see that guy as well. So alcohols, thiols, ethers, aldehydes, and ketones, again, using a wide variety of applications, and we'll talk probably about some of those as well. So let's talk about the functional groups of each of these. So an alcohol, the functional group for an alcohol is the OH group. So as soon as we see that OH group, we know that we are dealing with an alcohol. So we actually saw that in the reaction that we just looked at with our alkene. When we add water to an alkene, we bake a alcohol. So we just saw that basically when we have an alkene and we add some water, again, breaking that double bond, we'll turn this guy into an alcohol. This is, again, what is sometimes referred to as a hydration reaction, basically adding water, which is called hydration. This becomes an alcohol, and as we'll talk about here in just a second, that's 2 carbons, which is based off of ethane. Since it's an alcohol, we drop the last part and put OL like alcohol, and this becomes ethanol. So again, named very similar. We just saw phenol, and a phenol is basically a benzene ring that has a hydroxyl group. Again, remember that it is the benzene ring that has that OH group, or if you want to do the circle in there, you can as well. A thiol contains the SH group, so a sulfur-containing group. It's very similar to an alcohol. They share very similar sort of properties. And then our ether group is a carbon-oxygen-carbon run is our functional group. So functional group of an alcohol, OH, functional group of a thiol, SH, functional group of a ether is carbon-oxygen-carbon. Here's again some of those figures and line structure, condensed structure, and obviously the bond. But again, OH for our alcohol. This is our phenol because again, it has the carbox, has the benzene ring on it. SH, which is our thiol, and again, carbon, oxygen, carbon, single bonded all the way across in that order, gives us an ether. So the first real one we're going to look at is alcohols. So let's talk about alcohols and how we go about naming alcohols. Well, we go about naming alcohols pretty much the same way as we name everything else. We're going to be looking for the longest carbon chain that has the OH group in it. So when we do that, that again will be based off of those alkane names. We'll drop the E, and as it says here, replace it with the OL, and we will get our alcohol name. So as we can see here, we have 1 carbon with the OH group. 1 carbon, again, is based off of methane. Drop the E because of the OH, and it becomes methanol. 2 carbons. Two carbons based off of ethane. Has the OH group. Drop the E, becomes ethanol. At these 2 examples here, there's really no other place to put the OH group than say this would be carbon 1 or this would be carbon 1. When you get to 3 or more carbons in an alcohol, you do need to give the location of where the OH group. So that happens, for example, when we get to, say, 3 carbons here. We can put the OH group here. And this would be 3 carbons, which is based off of propane. It has an OH group, which makes it propanol. The location of that OH group is at carbon number 1, which makes it 1-propanol. 1, kind of like the double bond, triple bond thing, that gives the location of where we find the OH group. And that is because we could have the same 3 carbons, but put the OH group here. And this guy Would also have 3 carbons, which is based off of propane. It becomes propanol. OH group, though, is at carbon number 2, no matter which way you go. And that becomes what is known as 2-propanol, the location of where our OH group is at. Any questions on that? So much like double bonds and triple bonds, 3 or more carbons, we do need to give the location of the OH group. The OH group should get the smallest number, regardless of sort of which way you're going. You want to make sure it ends up at the smallest number. And then everybody else is numbered accordingly. So if there were some other groups attached, we would number those accordingly. You know, if we had like a bromine or something else attached, it would be numbered just like everybody else's. Any questions on that there? Now, in addition, we can also classify alcohols. And we could classify alcohols as primary, secondary, or tertiary, depending on sort of what is attached in terms of the OH group. And what I mean by that is, if you remember when we talked about primary carbons, that's basically a carbon attached to another carbon. So when we talk about a primary alcohol, we would be looking at the carbon that has the OH group attached, which is this guy. And we would want to know how many carbons are directly attached to it. And in this case, it would be 1. This would be a primary alcohol. Sorry about that. Primary alcohol. Now, if we have a carbon such as this one, when we look at the carbon that is attached to the OH group, that carbon has directly attached to it 1 carbon and 2 carbons. This would be known as a secondary alcohol. It's not like writing on this slide, apparently. Secondary alcohol, sorry about that. Secondary alcohol. Now we could also have a tertiary alcohol. So we can have carbon that has the OH group, say attached to here, or attached to here, and attached to here. And in this case, we would look at the carbon that has the OH group attached to it. And again, attached directly to that carbon is 1 carbon, 2 carbons, and 3 carbons. That's going to give us a tertiary. Wow. Okay, so try that again. Tertiary. All right, not getting better. Tertiary alcohol in this particular case. So when you're trying to identify a alcohol as primary, secondary, or tertiary, you look at the OH group that's attached, the carbon that has the OH group attached, and how many carbons are directly attached to it. Any questions on that there? Okay. Why don't you take a second here and see what you come up with the name. Go for longest carbon chain that has the OH group, give the OH group the smallest number, and name any groups attached the same way. So take a second and see what you come up with. Okay, so we're looking for, again, the longest continuous carbon chain that has the OH group. So in this case, I think just straight across will do it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's a couple of ways you could do it. I'm just going to take the straightest, which is just straight here. Again, having that OH group attached to it. So dissecting this name here, we got, what did I just say there? 6 carbons. So 6 carbons is based off of hexane. Because it has this OH group, it now becomes hexanol. We want a number to give the OH group the smaller number. And you could probably just see by looking at it, if we go right to left here, we're going to do that. Again, if we went the other way, the OH would be a much larger number. That would be 2-hexanol for the location that we have here for the OH group. Because we had to lock in the numbering going in that direction, that means the other group that's there, which is our methyl group, would be at 5-methyl-2-hexanol. Any questions on how that name came about there? So why don't you try a couple more here? And also, why don't you draw the structure for 3-methyl-2-butanol? And also, why don't you do, why don't you try 3-methyl-cyclohexanol? All right, take a couple minutes and see what you come up with here. Okay, so let's take a look and see how we're doing. So again, we want the longest chain with the OH group. So again, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You can get it a couple of different ways. We'll just take the straightest. Again, that contains the OH group. So longest chain there is 5 carbons. So 5 carbons would tell us it is based off of pentane. It now will become pentanol, OL at the end. Again, we want to give this OH group the smaller numbers. So going right to left should do that for us. That is going to then tell us this is 2-pentanol, where the OH is located. And because of that, our methyl group now will end up at carbon number 4. So putting all that together, that's going to be 4-methyl-2-pentanol. Any questions on that name there? Looking at B, we actually have a benzene ring here. So as we were just talking about, benzene ring with the OH group, that is going to be our phenol, right? So that was that special sort of benzene guy that has the OH group. Because of that, this guy definitely would be carbon number 1, which means that would probably be carbon 2, and that would be carbon 3, giving the bromine now the smaller number. If we went clockwise, it would have a much larger number, and that would mean that this is 3-bromophenol. We can bridge the gap there. No dash, but all together, 3-bromophenol. Any questions on that name there? Now, when we have our name and we want our formula, just like we've talked about before, we want to work backwards. So butanol, the OL tells us it's an alcohol. The 2 tells us that's where the OH group is at. And the but tells us it is 4 carbons. So starting with 4 carbons here, actually, I'm just going to draw it here. 1, 2, 3, and 4. Because you're drawing, you could go whichever way. I'm going to go left to right and call that carbon number 2. Because I went left to right, that means carbon number 3 would be right next door, and that would have a methyl group. Just like we did with all the other stuff, everything else is going to be hydrogen to get everybody to 4 bonds. So he needs 3, he needs 1, he needs 1, and he needs 3. And there you go. That would be this structure. Any questions on that particular one? Same idea here. We're going to work backwards. So cyclohexanol. Cyclo tells me it's a ring. Hexane tells me it's 6 carbons. OL tells me it's an alcohol. So that's an OH. Hopefully you can see the difference between these two. Double bonds here, no double bonds here. So that is cyclohexanol. Because of this, this is going to be carbon 1, which means I could go clockwise or counterclockwise here. I'm going to go clockwise, so that would be 2. This would be 3. And that is where I would put my methyl group. I wouldn't write it probably. I would probably just write CH3 would probably be good, or I could just stick the line out there if you want. CH3 would be better. There you go. And because this is sort of line structure, no real need to put any hydrogens in. Any questions on how to name an alcohol or draw the formula? By the way, if we look at this alcohol here, this carbon, which has the OH group attached to one carbon, 2 carbons, this would be a secondary alcohol. This carbon that's attached to the OH group is attached to 1 alcohol, 2 alcohols. This also would be a secondary alcohol. This guy here would also be actually a secondary alcohol as well. So again, that's how you number those guys. Any questions on that? All right. So we talked about some of these things. So ethanol is basically ethyl alcohol. That's the alcohol, if you will, and it's made by fermentation of glucose. We get our ethanols form here and our CO2. We actually can make an alcohol or ethanol by adding water. This is again the reaction that we just saw earlier. Double bond becomes a single bond. We add an H and an OH, and again, we make that ethanol here in this particular case from ethene, which is basically from ethane, right? So ethene, adding water through this hydration makes an alcohol, which is ethanol. These are some phenols. Again, more OH groups here. These OH groups are polar, which allows them to do hydrogen bonding. So alcohols can be very soluble in water because when it interacts with water, water is positive on the hydrogen, negative on the oxygen. It can do hydrogen bonding, which is that intermolecular force. And alcohols about 6 carbons and less are actually really soluble in water. If you get more carbons than that, the solubility really starts to decrease. One way you can increase the solubility is having a lot of OH groups, like this particular compound here has a lot of OH groups, and everywhere there's an OH group allows it to interact really well with water. Ethylene glycol is again a double alcohol here. It's basically antifreeze. And again, it's what basically in your car increases your boiling point so your car doesn't overboil, also decreases your freezing point so your car doesn't basically freeze as well. And again, it interacts really well with water as well because of these OH groups here. Here's some other guys here, not so important. But let's talk a little bit about a couple of the reactions that alcohols undergo. So we talked about basically making an alcohol by adding some water to it. And this may be a little bit out of order in terms of your notes. I think it might be towards the end of your notes where you'll find these slides. Hydration is when we add water to it. A dehydration is basically when we remove water. It's basically the opposite reaction. So we're going to take off a hydrogen from one carbon and an OH from the other, just like we put on a hydrogen and an OH. When we do, that's basically where water comes from. And if we get rid of that water, usually involving an acid and some heat, we basically will put the double bond back on. Everything else is exactly the same. Hydrogen there, same hydrogen, hydrogen there, same hydrogen, and hydrogen here. So a dehydration reaction is basically when we remove water, put the double bond back in. Hydration reaction is remove the double bond, put the water in to make the alcohol. So it's basically an opposite reaction. Just like when we put the hydrogen on the one with the most, we then would remove the hydrogen from the one that had the most, you know, going kind of the opposite way if there was kind of more than one choice. Let's though talk about a couple reactions that are important, which is an oxidation and reduction reaction. Oxidation reactions basically increases the number of carbon-oxygen bonds, and a reduction reaction reduces the number of bonds between carbon and oxygen. And when we talk about oxidation, there's kind of three definitions. It's like losing electrons, adding oxygen, or losing hydrogen. Reduction is basically the opposite. It is gaining electrons, losing oxygen as you go from reactants to products, are gaining hydrogen. So those are kind of three definitions here. In organic chemistry, we look at these definitions, the adding and losing of oxygen or hydrogen. And let's talk about what happens in an alcohol. And it depends on the type of alcohol. So what's going to happen is in a primary alcohol, which is what this guy is, there's a carbon that has the OH group attached to it directly is one carbon, and that was what makes it a primary carbon. We're essentially going to remove H2. So basically, we're going to remove H2, two hydrogens. Where is it going to come from? It's going to come from the carbon-oxygen bond. One hydrogen from there, and one hydrogen for there will go away. And then you make a double bond between the carbon and the oxygen. So that's exactly what happens. Again, nothing changes. We have 1, 2, 3 hydrogens, 1, 2, 3 hydrogens, and a carbon, absolutely the same. We have a carbon, same carbon. We have an oxygen, same oxygen. And we have one hydrogen, one hydrogen. What did we remove? We removed exactly what I just said. We removed one hydrogen from the oxygen, one from the carbon, and we double bonded those two. And when we do a primary alcohol and goes through an oxidation, which is sometimes abbreviated with this symbol, it makes what is referred to as an aldehyde. An aldehyde has a functional group of this, which is carbon, oxygen, double bond, and hydrogen. So the oxidation of a primary alcohol results in an aldehyde, hydrogen from the oxygen, hydrogen from the carbon that's attached to the oxygen, double bond the carbon, oxygen, don't change a other thing than those two things. Any questions on that reaction? All right, so